lecture, we covered many and some theorem about the sets and theory. As I remember, okay. Here, that's why today's date is 21. 2002 Discrete. We were on that part as a algebra and duality. You can hear my voice, right? Of sets and duality. Okay. I don't know reason. Okay, let's try to share the sets under the operations of union. Intersection. Section. And complement. And complement. Satisfy various laws. Various laws. Identities. Which are listed as below in our table. So first one, idempotent laws is a 1A. We know that one A union A is equal A. And as a B, 1B. Good morning, Emre. A intersect A is equal A. As a associative law, this second A union B in parentheses union C is equal A union parentheses B union C. And there's it to be A intersects B intersects C, A and B in parentheses. And there is equalities A intersects in parentheses B intersects C. And commutative laws and already we saw some part of the properties, and there is the commutative laws as a 3A, A union B is equal 3A, A union B is equal B union A. Of course, we can say for 3B, A intersect B is equal B intersect A. This is like, duality of union and intersection operation on set. And distributive laws is a for A. Okay, A union in parentheses B intersects C is equal A union B in parentheses intersect A union C. So union can be distributed on intersect. And let's look at the reverse. Is a for B, A intersect in parentheses B union C. Of course, we can say as A intersect B as the intersection of the two sets, union A intersect intersection with the C set. So there is identity clause, and we saw also identity clause in our chapter, some part. As a 5A, A union empty set is equal A. The 5B, A intersect with the universal set. This is equal as A. And 6A, A union A union universal set is equal universal set. And as a 6B, A intersect intersection with the empty set is equal empty set. So evolution laws is a 7 there is only set A complement, and again complement will be is equal again set A. And complements laws as a 8A case 8A, A union complement A is equal universal set, and 8B A intersect with the complement of A is equal empty set, and 9A, this is kind of summary also, 9A universal set complement is equal empty set, and 9B complement of empty set is equal as a universal set. So please don't confuse universal set and union symbol. Here is the A union universal set is equal universal set, and here is also this one to make like one more line to the right side of universal set like that. Is there any more? Yes, here is universal set. Okay, now it is better. And next one is a De Morgan laws. So if this is 10A, there is the A union B in parentheses, and there is a complement. This is equal A complement intersection B complement. Of course, the reverse is a 10B if there is the A intersection with B in parentheses as a complement. This is equal A complement union B complement. So these are the some summary of last lecture also. And as you see, the Morgan laws, like the logical law, and maybe we can mention about some theorem in that chapter. And there is the explanation in your book as A union B complement is equal if there is the X element is not element A or B, A or B set, and X, which X is not element of A and B set. So this is equal A complement intersect B. This is the different notation to show the Morgan laws 10A. Also, we will see some details in maybe logic chapter. And what else? And let's see something more for the duality. Okay, if there is the universal set union, no, intersect A union B set intersection with the A is equal A, and empty set union A intersection B union A is equal A. Okay, this is the page one. Continue with the finite sets counting principle as a new title. Let's see what is in that part. And in counting theory, we need the finite sets and counting principle, the definition. The page 2 for today's lecture. Okay, finite sets in counting principles. Okay, sets, of course, can be finite. There is the boundary for the element, or infinite, right? There is a two probability for the sets. Maybe there's so much element inside of the sets, and we can say this is a countable set, and we will say as a finite, or there could be infinite elements inside of the sets. So let's say a set S is said to be finite if S is empty, or if S contains exactly m elements where m is a positive integer. So there is a countable set member, then we will say this is a finite. Otherwise, S is infinite. Okay, let's try some simple example to get the idea. Okay, the set A of the letters of English alphabet and the set D of the days of the week are finite set, right? For alphabet, if we want to show do we know the representation? Okay, let's say we know, for example, set A, member of set A is equal to 26, and member of the B as a 7. So we can say these are countable, and according to that, these sets are finite sets. Okay, let's, as an example, E be the set of even positive integers, and there is also one more set like this. I let I be the unit interval. So we have two sets for that example. First one as a capital E. There is the, positive integers, even positive integers like 2, 4, 6, 8, and more, goes like that. And there is the I set, and it is representing intervals, let's say 0 to 1. So, which means represent like that x, which is equal to 0, greater, and less than, and is equal to 1. So, for both E and I, and we will say E and I are infinite. So we saw as a finite set as a and B. We saw the E and I as an infinite. And there is also one more approximation to give some idea as a countable and uncountable condition for the set. Let's find that idea as set S. We have as a set as a S is countable if S is finite, or if the elements of S can be arranged as a sequence. For that two conditions, we will say this is a countable set, in which case S is said to be countably infinite. So two conditions: countably finite set, countably infinite. Otherwise, as a other side, S is said to be uncountable and for that example, E as a countably E set E is countably infinite set, and I is uncountable infinite set. So actually, we define the number of the elements representing the so this is not correct. So here is the n. S is the different book notation. This should be n. I'm sorry. So counting elements in finite set. In finite set. The notation, actually I showed the notation. NS, or there's a second way to like absolute value line inside of the will denote the number of elements in a set S. So there's some different notation also, and so there is this some lemma for that condition as a lemma 1.6. Suppose A and B are finite disjoint sets, then we will say A union B is finite also, and then we will say number of A union B is equal number of set A and number of set B as a addition. We have that equalities. Okay, any question? So we have some okay, we have some more title to complete chapter 1. Anyway, we have time. Also, I asked the department to do some extra lecture for next week. If I get some extra lecture hour with you, I'm gonna be happy to cover some more part to exactly complete in that term. Okay, and thank you, Emre. The next one is a lemma 1.6. 1.6. Again, suppose S is the disjoint union of finite sets like A and B. Number of S is equal number of A plus number of B. But we have to point as a disjoint. So what you said, Nevlu Rahman, will the extra terms be online? Yeah, we will do maybe, I offer the 2 more hours for next week as a lecture. And if they accept, I mean, the planning department put to some extra 2 hours, you will see in your schedule. Okay, don't worry. Okay, let's continue because we have some critical explanation. Yeah, it is coming. Do we need any proof? Let's see. We need any proof. Okay, I won't consider any proof for that condition. Let's write the corollary 1.7. 1.7. Yeah, I saw, but I don't know what I'm gonna do for, you know, that night lecture. Let A and B be finite sets. So this is important part. So this is important part. Number of A difference B number of elements for A difference B, number of A minus number of A intersection B. So you know that meaning, right? We have two finite sets, A and B, and I'm looking for the number of sets A difference B. It means if there's the intersection between A and B, I will do minus number of A intersection B from A. There is the example for that condition. Suppose there is the art class. A has, or art class has 25 students, and 10 of them are taking a biology. 10 of them are taking a biology class B. Then the number of students in class A which are not in class B. So number of A difference B is equal number of A minus number of A intersect B. This is equal to 25 minus 10. This is equal to 15. Okay, 1.6 is a new information, is a corollary 1.6. And let's say A be a subset of a finite, again finite universal set that U, then these are really important. Number of A complement is equal number of union set minus number of A. Do we need any example? No, this is really easy and clear. So now important title. Okay, you have to keep that information in your mind because it is confusing our mind, especially for the students. Inclusion and exclusion principle. So this is important. We make it star, left and right. If there is what? There is a formula for an A union B even when they even when they are not disjoint. You know the meaning of disjoint, right? Called the inclusion and exclusion principle. So what was the meaning of disjoint in Turkish? Okay, yes. There is no common element, right? For that two sets. Yes. So theorem 1.9 as a inclusion exclusion theorem. Suppose now we will do something as a mole. In that case, A and B are finite sets. Then A union B and A intersection B are finite. And now number of is there any something more? A number of A union B. I'm waiting sometimes the streaming of the movie A union B is equal number of A plus number of B. So we have to do something as a more if these sets are not disjoint, we have to write to make some minus as a number of A intersection B, right? I hope so. So did you get that meaning? The example, you can make the example. We have as a, as a university student set as a U, and there is the two class as a A and B. Class A is like the discrete math, and class B like the programming. I don't know. It is the class B. Okay, here is the 15 students, and here is the 10 students, and here is the 30 students. So you can see from that diagram exactly, and see from that diagram I'm looking for as a number of A union B. So what is the number of A? Actually, number of A is equal 25. Number of B is equal 40. So I'm looking for that number to, you can see easily here is the intersection in 10 students. So, but if we don't know A plus B minus intersection, then we will get the correct answer. So number A 25 plus 40. Actually, if we don't do any minus for the intersection, we will get 65 students, but there is no 65 students because there is the 55 students as a totally. I have to do the minus of intersection, then I will get correct student number as a 55 in that university. Okay, 55. Okay. Did you get that? Ah, on that diagram, it is easy. Yes. So let's make it that condition as a tree set. Let's say we have tree set in our page 4. We have as a corollary 1.10 Now we have three sets, A, B, C are finite sets. Otherwise, we can talk about if there is infinite sets, we can talk about the number of sets. Again, A union B union C set also finite. So number of A union B union C is equal number of A. So I don't know exactly detail these sets. The common elements, or there is the disjoint and something else. I don't know any condition for that properties of these sets. So I know that inclusion and exclusion theorem. If I have three sets, I have to do minus for intersection AB minus intersection AC minus intersection BC plus, okay, I need more place, but I'm writing the here A intersect B intersect C. So is that clear? We make it 3 plus as an example to see in Venn diagram. We have 3 side, 1 is a plus, 2, 3, this is the universal set. Is a U, A, B, and C. Okay, let's say here is the 10, 5, 2, 3, 20, 4, and 15. So what's the number of A? Is 20. Number of B is 32. And number of C is what? 24. So can you say A union B union C as a number? Is it totally of the three sets exactly? No, right? If you add them together, it is going to be 52, 72, 76. What is the total number of universal sets? Actually, 59. Yeah, we have to do that formula as a number of A union B union C. So number of element A is a 20 plus 32 plus 24 minus. So A intersect B. What I have for A intersect B as a number, 8, right? Okay, 8 minus number of A intersect C, I have 5. and minus B intersect C, there is the 7. Then I will add what? What should I add here? 3 because of A intersect B intersect C. I have to add here as a 3. So I will get here as a 59. I think 59. So what that theorem is explaining to us. So you see, if I do minus, for example, A intersect B minus as a 8, you see I make it 3 as a one more time minus, then I have to add 3 back again to my total value. That's why I'm doing the minus as A intersect B, A intersect C, B intersect C. Then I'm adding that 3 because I'm doing the more than 1 times 3 from the whole set. Then I will get 59. If you add that numbers, you will see as a result. Okay, dear friend, let's do break. Okay.